Sorry, a bit of a late start today. Good, so today we're going to talk a little bit about hidden unit dynamics and then about convolutional neural networks. So we'll talk a little bit about the geometry of hidden units and the limitations of two-layer neural networks, the problem of vanishing and exploding gradients, alternative activation functions, methods for avoiding overfitting in neural networks, and one of which is dropout. So one way to understand the geometry of two-layer neural networks is to look at what's called an encoder task. Now, we're looking at this for two reasons. One, because it just allows us to start to understand the geometry of neural networks in a fairly simple setting, and also because this is a very simplified version of what are called autoencoder networks, which we'll get to at the very end of the course. The idea here is you have an input, you put in an input, and the network goes through a hidden layer and then an output, and it's trying to reproduce the same input. So the target value is the same as the input, so the task is actually trivial, but the interesting thing is that the activations have to go through a smaller number of hidden nodes in the middle, so there's this kind of bottleneck in the middle, and this forces the information to somehow be compressed inside the network. So we look at how this compression is achieved, and so I'm just going to draw, so we use what's called a 1 in n encoding. So however many input nodes we have the same number of input patterns as nodes, and for each input pattern here, one input has a value of 1 and the others have a value of 0. So this is sometimes called a 1-hot encoding because one of the inputs is hot and the others are not. Or it's called a 1 in n encoding, right? So if we have 5 inputs, there's just these 5 patterns, and as you can see, the target outputs are exactly the same as the inputs. So if we can see this on the document camera, let's have a look here. Okay, so in end-to-end encoder, and here we assume that there are 2 hidden nodes. So what we're trying to plot here, we're trying to take the weights of this neural network and plot them in a graphical way. So if there are 5 inputs and 2 hidden nodes, that means we have 10 weights in the input to hidden layer, because every input is connected to both of the hidden nodes, and then with the bias, that gives us actually 12 weights, and then with the output, we have 2 going to 5, so that gives us, again, 10, but with the bias gives us 15. So there's sort of 27 weights in this network, and we could just write them out as a list. We could write the values, but we get a better understanding of the situation if we try to graph these things. So let's first assume that there are just 2 inputs. So the way we do this is the following. For the input to hidden weights, I should have said the activations here of the hidden weights are tan h. So they're bounded they're sigmoid units. So they're bounded between 0 and 1. So this is a graph. Any activation of the hidden units can be represented on this graph. So it's a little bit like the graphs we were looking at last week when we were looking at the perceptrons. So this is the first hidden unit is along this axis. This is 0 and that's 1 if it's a sigmoid function, or -1 and +1 if it's tan h. And the second hidden unit is bounded between here and here. And so one way to display these weights is to say, okay, well, let's say that the first input is active. So that the one hot encoding, let's say the first input is 1 and the other inputs are 0. Well, then, and you ask, like, let's plot on this graph what the value of the hidden nodes would be for that particular input. And this basically tells us those input to hidden weights. Because, well, it's sort of mixed in a bit with the bias, but that input, well, let's suppose there's no bias. Just to keep it simple, let's assume there's no bias. Then, because the first input is 1 and everything else is 0, the hidden unit activations will simply be the hidden unit activations will effectively tell us the weight from that first input to each hidden node. But then with the sigmoid, with the activation function applied. So whatever the weight is that connects the, sorry, let me just go back to this for a second. So if this input is 1 and all these others are 0, and we're looking at this hidden unit, so this gets multiplied, 1 gets multiplied by this weight, and all the other weights get multiplied by 0, and we assume there's no bias, so actually it's just the value of this weight, and then afterwards you apply the transfer function, and that gives us this coordinate here, and the same thing for the other hidden unit. So we can actually use this as a mechanism for plotting the input to hidden weights. And then if we have another hidden, so let's look at the second hidden unit, the same story. This coordinate is just the weight from the second input to the first hidden unit, and then the sigmoid applied, and the same thing here for the other hidden unit. So the weight could be anything. The weight is unbounded, but once you apply the bounded transfer function, it brings us back into this square. We can't escape from the square. Now, so that's the input to hidden weights. Now, what about the hidden to output weights? Well, it's convenient to draw these as a line, and this again goes back to what we were doing with the perceptron. But remember, this is sort of like a perceptron. The top layer of the neural network is kind of like a perceptron, but it's being applied to this hidden unit space. And so the line shows us where it draws the boundary line between where that linear combination is negative and where it's positive. And because we're applying the sigmoid, if the linear combination is negative, the output will be less than 1/2, and if it's positive, it'll be bigger than 1/2, right? So these points represent the input hidden weights, and these lines represent the hidden to output weights. And then we can sort of try to figure out what these activations would look like if it had successfully learned this task. So let's start with the simplest cases where we have just 2 inputs and 2 outputs. And what we want, well, basically you would end up with something like this, that, well, this is a bit too trivial. Let's say you've got 3 inputs and 3 outputs. It'll try to get into a configuration where, well, this line should be, because you see the outputs are one hot as well as the inputs. So what should happen is this line each line should divide 1 point from the other points. So you should have one line. This should have the property that this point is on one side and the other point's on the other side. This should do the same for that point, and this should do the same for that point. And so if you want to get the sort of maximum separation, so you can train the thing for a long time and plot the result, and what you end up with is something kind of like this. These points get as far away from each other as possible, and then the lines try to divide one point off from the others. And I think you can see if you add a fourth point, you're going to get this kind of configuration. And then when you add a fifth point, the thing starts to has to bend around a bit in order to kind of accommodate this. But what you end up with is basically an attempt to fit a 5-pointed star into a square as best you can. So it is possible like this, and you can keep going and try to fit, have 6 inputs, 7 inputs, 8 inputs. It sort of can be done, but the accuracy gets lower and lower the more points you try to add. Right? So as I said, it's a trivial task, but it is interesting just in terms of helping to kind of visualize the geometry of this hidden unit space. Any questions about this? Okay, and you can sort of think about this in higher dimensions as an exercise. Try to imagine if you had 8 inputs and 3 hidden nodes and 8 outputs, and you did the same task, what kind of geometry would emerge in 3 dimensions? So just kind of have a think about that yourself. Okay, so that was a very, very simple task. Now we can apply scale up the same kind of ideas to more serious networks. This is still a 2-layer neural network, but on a much bigger scale. This is a picture from a network that was from early work in autonomous driving. By Pomolo's group in Pittsburgh, and they have. The task, this dates back to about 1990, they had a task where they have a car or an SUV that tries to drive itself autonomously, and one of the sensors that it has is a camera mounted at the front of the vehicle, and it produces an image that's 30 by 32, and it goes through a number of hidden nodes and then produces an output, and the output here is trying to decide which direction to steer the car. And basically you take a weighted average of these outputs. So the middle node means that you should have the steering wheel so that you're pointing straight ahead. The node on the right means that you're turning sharply right, and the node on the left that you're turning sharply left. And the other nodes represent kind of patterns in the middle. And I won't go into all the details. It's sort of interesting how they trained this as well. They got a human to drive the car and collected a lot of training examples for supervised learning. When the image looked like this, the human chose this steering angle and so on. And they had a few extra enhancements to get it to learn properly. In fact, the first time when they first trained it just on the human data, it actually didn't do a very good job. And what they realized was the reason it didn't do a good job was the following, that it couldn't drive quite as well as the human. So over time, it would gradually drift, pointing at an angle off the road, and then it would get into a situation that the human had never gotten into. And because the human had never encountered that situation, there wasn't any training data to cover it, so then it would go further off the road. So it was unstable, and they actually solved that by creating synthetic data. So they used knowledge of the task domain and said, well, okay, with the road in this configuration, the human shows a steering angle of 10 degrees. Let's suppose that the vehicle is pointing at a slightly bigger angle. What would the image look like, and what angle would the human choose in that situation? So they create this kind of synthetic data that never actually occurred for the human, and when they threw in the synthetic data, it was able to learn successfully. So this is interesting because it's an early example of what's called data augmentation. Data augmentation is creating additional synthetic data based on knowledge of the task domain. And when we get to image processing, we'll talk about another example of data augmentation. Okay, now, but what about this? The diagram here, so this is what's called a Hinton diagram because it was developed by Geoffrey Hinton, and the way this works is as follows. The bottom square thing here represents the input to hidden weights for one of the hidden units. So here we've got, they had various generations of these. They had 4 hidden units and then 10 and then 20, but in this early example, they only had 4 hidden units. So this diagram is for one particular hidden unit, and then you can create similar diagrams for the other 3. And each blob here represents one of the input, one of the weight from one input to that hidden unit. And I think the white dots are positive numbers and the black dots are negative numbers. And so you can kind of get an idea what sort of image this hidden node would respond most strongly to. And the line at the top represents the hidden to output weights, again for the same hidden unit. So you see there's 30 outputs, so you've got 30 numbers there. And so you can see this unit, if this unit is very active, then it means that the network would be likely to steer strongly to the left. And when we look at these pictures here, it kind of, in a way, it sort of represents a kind of pictorial situation in which the network, in which that node would have a high, it kind of gives you an idea of what sort of image would cause that hidden node to have a very high activation, but it's not necessarily a specific situation. It can be a superposition of multiple images, right, or multiple situations. So this, what this is saying is, if the, let me see here. So if the road is black, I guess the road is, if we assume the road is darker than the surrounds, then yeah, if the road is sort of in this configuration, then you would be steering, if the road is in this configuration, then you would be veering to the right, so you'd have to steer sharply to the left to get back on the road. So it's not sort of, it's not always, because of the superposition, it's not always easy to translate this into kind of defeasible reasoning or defensible logic, but it does give you some idea how the network is actually achieving its objective. I mean, I might just mention in passing this issue about the road. when they did the DARPA Grand Challenge in the early 2000s, they were driving through the desert, and sometimes the road was darker than the surroundings, and sometimes it was lighter. So parts of the route, the road had bitumen and looked dark, and there were other parts where it was like a dirt road. And that was one of the things they had to do, is if the vehicle drove across a transition where the road was dark and suddenly it became light, it had to detect that and very quickly switch from one network to another so that it wouldn't get confused. Now this is some other early work. Well, this is from the 90s. This is some early work in face recognition and pose recognition. So these networks are very, very primitive by modern standards, but again, they're interesting from the point of view of understanding the geometry. So they had a number of different people, and they took photographs of these people so that you can train a network to try to detect different aspects of these photos. So first of all, the identity of the person. Secondly, things like whether they're wearing sunglasses or not. But in this case, you're trying to detect which direction the person is facing. So you take photos of all these people facing left, right, up or down. And again, it's a pretty low resolution image, 30 by 32, only 3 hidden nodes, and then 4 outputs. And the outputs are trying to classify whether it's up, down, left, straight, right, or up. And the classification is done by softmax, which we'll talk about in a minute. But basically, you try to get the correct output to have a high activation, and the others to have a low activation. And if you draw Hinton diagrams for this task, this is kind of what it looks like. So here we've drawn the weights. So we've only got 3 hidden nodes. So each of those kind of phantom images corresponds to 1 hidden node. And then the weights at the top also correspond to the input to output nodes. So it's been the input to output nodes have been grouped by the output. Yeah. And again, you can see that it's a superposition. I'm not sure why they had 3 hidden nodes and not 4, but you can sort of get a bit of an idea here if someone is looking left. Well, let's have a look here. Yeah, if someone's looking to the right, you would expect brightness here and darkness there because of their hair. And so this hidden node would probably be quite active in that situation. Whereas this one is more, yeah, so this one is kind of is a bit white at the top, but dark on the left, and this is white here and dark here, and this is more symmetric. So somehow, these are sometimes called eigenfaces, these images, because geometrically they might represent the principal components of all these images in hidden unit space. Now, what else can we say? Just sticking again with these 2-layer neural networks, what else can we say about them? Well, there's a lot of interesting symmetries involved here. So if you, going back to here, we've got 3 hidden nodes. But if I were to swap the first 2 hidden nodes, let's suppose I was to swap the first 2 hidden nodes. So all the weights that currently go into the first hidden node are now those values are going to be used for the second hidden node and vice versa, and all the nodes coming out of this first hidden node, I swap them with the nodes coming out of the second hidden node. If I were to do that, you wouldn't notice any difference in the behavior of the network, because the first hidden node would compute exactly what the second hidden node used to compute, and the second hidden node would compute what the first node used to compute, but then the output nodes would swap the roles of those two hidden nodes. And so that value of the hidden nodes would be swapped around, but the value of the output nodes would be exactly the same. And you can, in fact, permute the hidden nodes in any order. So if there are 10 hidden nodes, there are 10 factorial, which is about 3 million different ways to permute those nodes. But you would get exactly the same, the behavior of the network would be exactly the same. Assuming symmetric trade. So it's easier to see this if you use the tanh transfer function. You just have to negate the weights, right? If we were to use the sigmoid transfer function in the hidden nodes, you have to fiddle around a bit with the bias because of the thing's not radially symmetric, but you could achieve the same kind of symmetry. Now also, again, assuming the tanh transfer function, we could swap the sign of a hidden node. We could say, okay, this first hidden node, I'm going to take all the weights coming into that hidden node and I'm going to make each one negative of what it used to be. And the weights coming out of that hidden node, I say, are the negative of what they used to be. So then these images here would just become negative, so the black parts would become white and the white parts would become black. But because we've swapped the weights both of the coming into the node and going out, again, the output would be exactly the same. So that's another kind of symmetry. So again, if you think, if I got 10 hidden nodes, there's 2 to the power 10 ways to choose fiddle the signs of the hidden nodes. And so if you give me, this helps you to try to start to understand the vastness of these high-dimensional spaces. You know, if you give me one set of weights that perform this task well with 10 hidden nodes, I can give you 2 to the 10 times 10 factorial other sets of weights which also perform the task equally well. So I can give you 3 billion, there are 3 billion other networks that perform the task exactly the same as the one you gave me. Yeah, so there's sort of actually massive symmetry here. And if you kind of plot the way these things train, there's a kind of controlled non-linearity going on here. So when the weights are small, you're in the kind of linear region of that transfer function. So you get a function that's approximately linear. As the weights get bigger, the hidden nodes start to saturate, and it becomes like gradually more and more non-linear. So it's there's sort of an advantage here to the thing being, if the thing was fully linear, and this is, I've sort of set this as one of the exercises. If you had a 2-layer neural network, and you didn't have any transfer function, you only had a linear transfer function. When you compose 2 linear functions, you again get a linear function. So you wouldn't get any benefit out of the second layer. So it's no good to have something that's fully linear, but there's some advantage to have something that is mostly linear with a little bit of nonlinearity, but not too much nonlinearity. So this was, as I mentioned, like back in the old days, people tended to use these two-layer neural networks, but two-layer neural networks are limited in what they can compute. So as we mentioned, a one-layer neural network can only learn a linearly separable function. A two-layer neural network can learn a bigger variety of functions, but there are some types of functions that a two-layer neural network can't learn. And this is one example of a function which kind of really can't be learned by a two-layer neural network, but can be learned by a three-layer network. This is just a toy problem that someone came up with. I think it was Weigand who came up with this. You have two inputs, and the data consists of these two sets of points. So you've got the red pluses are the positive examples, and the blue circles are the negative examples, and you're trying to train your system in such a way that it will allocate, it'll output 1 for the pluses and 0 for the O's. And this was kind of, it was partly, this was partly made up as an example of how representations are important, because if you were able to translate, if you converted this input from XY coordinates into radial, if you converted it from Cartesian to radial coordinates, if you change X and Y to like the angle and the R and theta, then this task would be easy to learn. So but neural networks kind of can't see that, right? But it's also just interesting in terms of pushing the boundaries of what kind of geometry examining the limits of these two-layer networks, right? So you try to train a two-layer network on this, it won't succeed, but it is possible to train a three-layer network as shown on the right here. So we have the two inputs, and then we have the first hidden layer has two nodes, the second hidden layer has two nodes, and then there's one output. And we have like tan H transfer function at the hidden nodes and the sigmoid at the output. And even that is kind of straining things a bit, so it learns it better if we have introduced shortcut connections that bypass certain layers. So you notice there are shortcut connections going directly from here to here, and going from here to here, and from here to here. So there's always there's the full set of weights going from any lower layer to any higher layer, and it is interesting to look at these early models because these ideas have come back recently in image processing with dense networks and residual networks, or particularly dense networks. This in the modern terminology, this would be called a dense network. So it is possible to learn it with this three-layer network with shortcut connections. The training, you have to be a bit careful about the training. You have to adjust the learning rate and the momentum very carefully in order to get this to work, but it does work. And if you try to analyze how the task is achieved, the first layer learns linearly separable functions of the inputs. The second layer, it's a bit, we can't give a simple characterization of what kind of functions the second layer can learn, but roughly speaking, they can learn like convex functions. The boundary that's produced by that second hidden layer is kind of is convex but not concave. But then the third layer, by putting together these convex functions in the third layer, you can get this kind of concave function that separates these two classes. Yeah. So here's one example of successful training of a three-layer network. But so then naively you might think, okay, well, if I've got a complicated task that can't be learned with a two-layer neural network, I'll just keep adding some more layers. Maybe if I have 3 or 4 or 5 or 6 layers, the task may be learned. But when people first tried to do this in the 90s, they found that it's not as easy as you might think. So normally what happens is if you try to learn a serious task and you've got more than 2 layers, this gradient descent kind of fails. Now, I guess it fails because it falls into a local minimum, but to be more specific, you get what's known as the problem of vanishing or exploding gradients. So if the learning rate is very low, what will happen is, so you're presenting an output, you're presenting you feed in an input, you get the output, and you compare it to the target, and you have a loss function, and then you start back propagating. If the learning rate is low, you back propagate the differentials from here to here, and then here to here, and then here to here, and the size of those differentials will diminish every time you go back one layer, and they can kind of decay exponentially. So then you get the problem. By the time you get back to with 3 layers maybe okay, but let's say you have 6 layers. By the time you get back to the early layers, the differentials may have more or less vanished or become extremely small, and so the thing doesn't learn because the weight updates get concentrated on these high layers and not so many on the lower layers. Right? That's called the vanishing gradients problem now, but on the other hand, if you crank the learning rate up high, then you get the opposite problem, that as you go back through these layers, the differentials get bigger and bigger, and then they may, but then the learning may become unstable. The changes in the lower layers, may be so large that the weights kind of bounce out of the local minimum and might even become infinite eventually. So this is again, a lot of this is like places where the field got stuck at different places. So this is where we got stuck for a long time, this idea with the vanishing and exploding gradients. Now, there's a few ways. Eventually, people did discover some ways to get around this. I'll talk about some of them today, and others after the holiday next week. So one way to do this is to replace the activation function. Different activation functions, then weight initialization and batch normalization. So those are methods we'll talk about next time. Now, recurrent networks, later on in week 6 we'll talk about networks that process a sequence of inputs, for language or signal processing. So the same thing happens there with vanishing and exploding gradients, because if you receive a sequence of signals and the output might depend on something that happened some time ago, you need to have those gradients preserved long enough. So it kind of appears in a slightly different guise, but it's the same kind of problem, and there's specific ways to handle that. And finally, we've got layer-wise unsupervised pre-training. Right? So there's a number of different approaches to this. Right? We're just going to talk about the top one today. All right, so these are the two activation functions we talked about so far. These are all plotted on the same scale. This is the sigmoid, and this is the hyperbolic tangent. And when we plot them on precisely the same scale, you can kind of see, that the hyperbolic tangent is much steeper than the sigmoid. So it's been stretched in the y direction and also squashed up in the x direction. So the gradient's gone from 1/2 to 2. It's 4 times as big in the middle. This was kind of a radical idea, I guess, that was introduced, I think, by Alex Zielinski in Hinton's lab around 2010, is to actually use this as a transfer function. It's called a rectified linear unit, and this function is equal to 0 when the input is negative, and it's equal to the input when it's positive. Yeah, so it's just like the identity function composed with 0. And like, it seems a bit mad because first of all, the gradient here is 0, and secondly, there's that sharp corner there. But somehow it turns out that in many applications this gives quite reasonable results. Yeah, so it's very common these days to use these rectified linear units. Sometimes we have what's called a leaky ReLU, where this left-hand side isn't quite flat, but the left-hand side might be, say, 0.2 times x. So there would be a slight gradient here, but much flatter than this. So, like I said, at first sight, this seems quite surprising that this would work. I guess, by putting together, there's been some analysis done on the geometry that emerges when you have these deep networks, rectified linear units. And I guess it kind of creates, in a way, a piecewise linear function in that high-dimensional space. The other thing about it is it's very fast to compute this. Because you're computing a multiple of x, or just x, that can happen very quickly. This is a fairly recent work, just a couple of years ago. Someone introduced this scaled exponential linear unit. So this is it's a multiple of x on the right-hand side and a decaying exponential on the left. And there's this little kink in the middle. And for some reason, this kind of does a reasonable job as well. But this is the more kind of standard one. And you can see the gradients are never going to vanish here, because if you're on this side of the equation, then the gradient is just gets multiplied by a constant. Okay, so like I said, that's just one way of avoiding vanishing and exploding gradients. We'll get to others as the course progresses. So the final section before the break is about avoiding overfitting in neural nets. So we talked about that whole thing with supervised learning and Occam's razor and overfitting. how do we avoid overfitting in neural networks? Well, one way is to limit the number of hidden nodes or the number of connections. So, as I mentioned with that autonomous driving example, we generally can't choose the number of inputs and outputs. We're going to adjust the number of hidden nodes. So you could have 4 hidden nodes, you could have 10 hidden nodes, you could have 20 hidden nodes, and if you have a smaller number of hidden nodes, then maybe that avoids overfitting. I should show you let me just try to make this a little bit more tangible here. So these are some examples of what happens. So remember, we have a training set and we have a test set. So you can do your training to try to reduce the error on the training set, and you can plot that over time, and you expect that it will decrease. So the dark line underneath is the training error plotted over time based on the number of weight updates. So if we have a certain amount of training data, every time we go through the training data, that's called an epoch. And so, here this is where we've been through all the data 5,000 times, and then 10,000, and then 15,000. Now, this, and then what's the other curve is the test set error or the validation set error. So you could plot the test error. You've got the training set that you're training on, and then you have a test set. And so what you're really interested in is the evaluation on the test set. Now, sometimes people have a division into 3, so they have a training set and a validation set and then a test set. So they use the validation set as a kind of pretend test set. And then sometimes they have another test set that they don't do anything with until the very end. So, but whether it's the validation set or the testing set, you get the same kind of behavior. And what you notice here, you often see this kind of pattern that the training error goes down. The training error continues to go down, but the test error goes down for a while and then either just flattens out or in some cases goes up again. You see how the validation set error is actually lower here than what it is over here. So, so this is another method. Another method to avoid overfitting is what's called early stopping. Early stopping. So you limit the number of weight updates. So you generate this graph, and then you say, okay, well, the validation set error got a minimum here, so I'm just going to train up to here and then stop. I'm not going to keep training any further, because if the validation set error is minimal here, then likely the test set error will be minimal here. So you can kind of see why the purists like to have this division into 3, because if I were to do this on the test set, it's a little bit, some people may complain, I've used the test set to decide when to stop. To be really pure in machine learning, you're supposed to not do anything at all with the test set, not get any information at all about the test set until at the very end when your network is finished. And so that's why we use the validation set to decide where to stop rather than a test set. And but it doesn't always, here's another example. Sometimes it works this way. So here, the training error was kind of flat at the beginning and then went down very steeply, which is quite common actually in image classification tasks that we'll talk about next week or the week after. But here, notice the validation set went down, and then it went up again, and then it continued to go down. So you've got to be a bit careful about this. You know, if you only, let's say if you stopped your experiment here, you might think, oh, well, you know, this is the minimum of the validation set, so I should only train that far. But actually, if we keep going, there's just a bit of a sort of hump here, and then the validation set keeps going down, so we'd actually be better off to keep training out to here. So this just kind of gives you an example of some of the pitfalls to watch out for in different kinds of behavior in different sets. But the other thing I wanted to say, I mean, I didn't draw a separate graph of this, but the x-axis here shows the number of training cycles, but we could make a graph where the x-axis shows the number of hidden nodes. You know, you can sort of imagine a graph where we have 5 hidden nodes here and 10 and 15 and 20. We couldn't draw a smooth curve like this, but we could measure the error. We could have 5 hidden nodes, and we could measure for every number of hidden nodes, we could measure the training error and the validation error, and often we would get the same kind of curve in that situation. So if we were to do this and we saw this and we observed this kind of curve, then you would say, okay, the optimum number of hidden nodes for this task is 10. You know, if I've got 10 hidden nodes, I'm minimizing the validation set error, but if I go to 20 nodes, it's overfitting. So I don't want that. So that's often what we do, is we do experiments with different numbers of hidden nodes and draw these graphs and make a decision on that basis how many hidden nodes to have. Okay. So this kind of covers those first 2 cases, the number of hidden nodes and the number of training epochs. Now the other 2 are weight decay and dropout. Now weight decay we discussed last time. So if you remember, weight decay was not to do with the number of hidden nodes, but it was to do with the size of the weights. We introduced an extra loss term which encourages the weights to be small, and that often prevents overfitting as well. Yeah. If the training set error is the same but the size of the weights is smaller, then that often leads to better generalization. So it's again, you know, in statistics they often talk about the number of free parameters, and the complexity of the model is like determined by the number of free parameters, but in reality it's not always that simple. So if you have weight decay, you haven't actually changed the number of free parameters, but because you're putting pressure for the weights to be small, the model is simpler for that reason, yeah, conceptually. Okay, so finally we have dropout. Now this, so this is another method to avoid overfitting. So let me first explain what it is and then have a bit of a discussion why it works. So you remember that we normally train in mini batches these days because we've got parallel hardware available to us. So we may train in blocks of 200 training items at a time. And the way this dropout works is we say, okay, I'm about to train this particular mini batch, and the network I have is the one on the left, but I'm going to randomly, I'm going to randomly pick some nodes that won't be active for this particular training batch. So the ones that are marked as X are not included. Now, often it's just hidden, usually it's just hidden nodes, but sometimes inputs are dropped out as well. And you have to choose a certain percentage that's dropped out. You know, you may choose that 50% of the nodes will be dropped out, or 20% of the nodes will be dropped out. You know, you adjust this parameter, and so the networks that are, the nodes that are dropped out just don't participate in the training, and whatever nodes remain have to do the best they can to achieve the task. So you train that mini batch with these nodes dropped out. And then when you get to the next mini batch, you choose a different subset of nodes that are going to be dropped out. So every mini batch, you choose a different subset of nodes. Now, there's a neat trick about this. You know, you might say, okay, well, this is a problem because what am I going to do in the testing? You know, I've trained my network in such a way that some of the nodes are always inactive. So what am I going to do when I test the network? Should I still have some nodes be inactive, and which ones should they be? But here's the neat trick. So when I'm testing the network, or when I'm deploying the network after it's been trained, all the nodes are active, but the activation of each node gets multiplied by a weight. It gets multiplied by a factor that's the same as the dropout factor. So if during training 50% of the hidden nodes were dropped out, when you're deploying, all nodes are active, but every node has its activation multiplied by 0.5. Right? If in the training 20% of the nodes are dropped out and 80% are kept, then in the deployment every node is present, but every node has its activation multiplied by 0.8. Right? So that means that on average, it's very clever because all the nodes are present, but on average, the nodes are contributing, the full set of nodes on average are contributing the same amount of activation as 80% of them would have contributed when the others were dropped out. Right? So why is this? Why is this beneficial? Well, one way to look at it is the following. There's a couple of ways to view this, and there's a pretty good explanation of this in the textbook as well. It forces the network to achieve a redundancy because it must deal with a situation where some features are missing. So you can't, the network, it can't, it becomes more resilient, like it can't rely completely on a particular node because that node might be absent. So whatever job was done by this node that got dropped out has to be, other nodes have to kind of duplicate to some extent the information provided by that node. So you've got kind of redundancy there. And this is partly inspired by human biology, studies of the brain. Some nodes at various times are just inactive because they're, I don't know, taking a rest or something or other. Certain nodes, neurons might become inactive for a period of time, and other neurons have to be able to step in and take over their function. Not just, but it's distributed. So it's not like each neuron. It's not like one neuron is inactive and a specific other neuron takes over its role. It may be a collection of other neurons that collectively take over its role. Okay, that's one way of looking at it. What's the other way of looking at it? Well, dropout implicitly and efficiently simulates an ensemble of different architectures. So we just have to talk a little bit about some concepts from machine learning to understand this. So just speaking about machine learning generally, there's this concept of ensembling. That's for those of you who are not native speakers of English, because this is a French word, we pronounce the E's as if they were O's. It's pronounced ensemble, not ensemble. So there's this method called ensembling where you want to learn a certain task and you train multiple systems to do the same task, and then you somehow combine them together. So if you look, there are these Kaggle, over the years there have been these Kaggle machine learning competitions where someone offers a bunch of money to the team that can best achieve the best score for some supervised learning task, predicting the number of days someone's going to stay in hospital, or predicting how someone will rate, how people will rate movies or whatever. And if you look at the entries to that competition that do well, often they employ these ensembling methods. So you may train a few, 3 different neural networks with different numbers of hidden nodes. There's another thing called support vector machines. So you may train a couple of support vector machines with different kernel functions. So you've got 3 neural networks and 2 SVMs. And then if it's a classification task, you may just get all these, you've got 5 different models, you might get them all to vote on the class, and then if 3 of them prefer one class and 2 prefer the other class, you go with the majority rule. Or sometimes you add up the confidences or whatever. Voting is the most common way of doing this. And then the way these competitions work, as it gets closer and closer to the deadline, you may find that 2 teams who are both doing really well will agree to cooperate with each other, and whatever methods they're using, they'll ensemble them all together to achieve the final accuracy. So, and the idea is, if you can have a diversity of different models, that's even better. And then there's also this concept of bagging. Well, this is more to do with, this is related to ensembling. So this is to say, okay, well, let's say I don't have a diversity of models. I've just got the same neural network architecture. If I train it on the same data multiple times, there'll be a little bit of difference each time, but I can get a bit more difference if I change the input slightly. So there's this idea of so the way bagging works is as follows. Like, let's say you've got 100 training items. You imagine that those 100 training items are in a bag, and you randomly pull out a training item one at a time with replacement. So I pick out one training item and write it down, but then I put it back in the bag, and then I pick out a random item, and I do this 100 times. So some of them won't get picked, some of them will get picked twice. Occasionally something might get picked 3 times, but that's unlikely. But some of them will be missing, some will be picked twice, and whatever it is, I train on that set, and then I repeat the process. So each time I'm training on a slightly different training set, in the sense that some items are repeated and others are missing, and then I can ensemble those things. All right, so the last slide before the break. So this is another, right, so how does this relate to dropout? Well, you could imagine doing the following experiment. I have my neural network, and I want to do ensembling, and so every time I'm going to ensemble, but every time, with different architectures by doing the dropout. So I randomly pick certain nodes to drop out, and I get a reduced architecture. I train that on the training data, and then I pick randomly another subset to drop out, and I train that. So you could imagine this theoretical experiment where you train hundreds of models, and each model is created by dropping out a different subset of nodes, and then you could ensemble them together. Now, to actually do that would take too long. It'd be too computationally expensive. But if you analyze this mathematically, what this dropout is actually doing is like implicitly ensembling over those different architectures. So we're not training every architecture on all of the training data, but we're training every architecture on some subset of the training data. And then at the end, we're doing this averaging trick, and you can kind of prove that implicitly that's doing the same kind of thing as if you're averaging over all those different models. Yeah. So this is a very neat trick because it provides the benefit of ensembling, but in a very efficient way. Any questions about that? Good. Okay, we'll take a 10-minute break, and then we'll talk about convolutional networks. Yeah.
So what's the difference between transfer function and activation function?
Same. They're just, different terminology, yeah.
All right. The second question is, what difference is between shoulder and flag?
It's just, this is a local minimum because it goes up at both ends.
All right.
This one goes up on one side and down on the other.
All right, thanks.
Hey.
Professor Blake.
Yeah.
Sorry, is the microphone on at the moment?
I hope so. Are you having trouble hearing?
Oh no, I just wanted to...
Oh, sorry, no, I think it's muted.
Yeah.
Sorry, I think it's muted. I think it's often. Yes.
Regarding automation.
Yes, that's right. I do remember that.
Yeah, no, it's interesting. I've been wanting to talk to you about it ever since, but I couldn't get to class.
Right. Thank you. Yeah, I did talk more about these issues.
Yeah, I think there's a lot of strong opinions out there, often very uninformed.
Right.
And so I think it's a very tricky situation we're all in as a society.
Yes.
The economists don't really understand AI. I feel like the machine learning experts don't really understand the nature of the economy, not that the economists understand it either. It's just fascinating. But anyway, I don't want to interrupt.
Yeah. Look, if you send me another email, if you want to arrange a time to have a chat.
Yeah, I think that'd be great. I'd love to just gauge your opinions as well.
Yeah.
I went to the US actually to do a PhD in economics at Northwestern University. But it was actually very discouraging. So I never actually finished.
Is that right?
Yeah, I came back and started working at the
Because
RBA.
you thought they were too old-fashioned, or?
Yes. I decided while in my first year, not midway through, but AI has really exceeded even my wildest expectations. It took how rewarding it is. It's actually also thinking about human behavior. I found it fascinating.
MIT economists who wrote a book about this, right?
Yes.
One of them was that antivirus guy. McAfee? I can't remember.
I know exactly what you're talking about. Yeah, I know exactly what you're talking about.
Blanking on his name.
I know exactly what you're talking about. Some funny name. They were
It's
they were
like
at MIT
school.
for business school.
Yeah.
Yeah. They wrote a book on how the productivity revolution and stuff like that.
Yeah.
In the meantime, so it doesn't anyway. It's this weird bifurcation of wages and productivity.
Yeah.
Right? High skilled people's wage growth is crazy.
Well, that's right.
So it's
well,
not,
yeah,
you know, while all society wage growth is slow, you know.
I don't. Yeah, I mean, I don't think it's not inevitable. My view, it's not inevitable that technology will cause inequality, but people with a neoliberal philosophy have somehow managed to use automation as an excuse or a tool to achieve inequality.
I agree completely. I mean, I think, so the point I flagged with you in the email was that the corporate structures are a problem as well, because we have these kind of like corporations like Amazon, which
Yeah.
monopolizing, not just they're monopolizing the human capital. Because if you were to ask a group of all these students, would you work at Amazon and Google, or would you start your own shop? There are so many people that opt for Amazon and Google. And then they just end up monopolizing all the human capital. It should be the case that 1/10 of this class goes off to the government, 1/10 goes off to manufacturing, and random places too. Right? You should have a chief technology guy at the local grocery store or something like that. But if you don't, you have all the tech people concentrated on that, and then Amazon will just roll out 100,000 grocery stores. That's nuts too. Sorry, I don't.
No. Yeah, let's talk about that.
Yeah, I've been good. Yeah, thank you very much.
Yeah. I work on the some image processing, some language processing, and mainly the deep learning, and also some evolutionary computation. Yes. So each, like this point, like maybe so this pattern is 1 0 0 0, and then it gets mapped to here, and maybe 0 1 0 0 gets mapped to here, and that's 0 0 1 0 0 0 0 1. So from looking at these points, you can tell what all the input to hidden weights are.
So it's like coordinate system.
Yeah, exactly.
When it's up to like 5.
Yeah.
I always try to draw. I'm not quite sure if it's right. Yeah.
I think it's not quite the encoder, but maybe some other function. Yeah. See, for this line here, these two things would output 1 and these would output 0. So the pattern would be like 1 1 0 0 0.
Okay. I might have more.
Yeah, there's one of the exercises. Maybe have a go at one of the exercises, and you might be able to understand it better.
Some question about that.
Yeah.
I still don't understand how does this line represent the output?
Well, the output is a function on the space, and so if you kind of it's a linear function composed with a sigmoid. So let's say if you draw the line so that on this side of the line the function is bigger than a half, and on the other side of the line the function is smaller than a half. function would really have this kind of shape. The function would really look like this. If you plot it as a three-dimensional function, it would kind of look like this. So we're just drawing like, so you see how on one side it's less than a half and on the other side it's bigger than a half. So the function's really like this, but we just draw a line to show. Like this part here.
So this is actually a three-dimensional thing.
Three-dimensional, yeah, exactly. It really looks like this.
So like this is a coordinate system, and
Yeah.
like this is an axis. Yeah.
That's right.
And this line is about if the input is like at this side of the slide,
Yeah.
the output will be triggers the narrow activation.
That's right. Yeah.
Another thing is
Kind of like the text set, but we don't want to look at the text set until the very end. So we use the validation set. We train on the training set, but we use the validation set to tell us when to stop or how many nodes to have or something. So,
how do you get to the validation?
well, sometimes you have the test set and then sometimes it's given to you. Sometimes you randomly choose it yourself.
Randomly.
Well, you have a certain number of training items, but you use only 90% of them for training and the other 10% for validation. Of these Kaggle competitions, it's actually explicitly. Actually, it's interesting the way the Kaggle competitions work. You have the training set, and then once per day you can submit a. You have the training set and then the validation set. So the training set you are given the outputs. The validation set you're not given the outputs, you're just given the inputs. But once per day you can submit your network, your model. You can submit your answers for the validation set and it'll tell you how many, it won't tell you which ones you got right, but it'll tell you how many you got right. So it's kind of, and then they have a test set that they use at the very end that they have with separate components.
It's like a scaling tools to tell you how like the quality of your training.
That's right, exactly. It's like a pretend test set.
And like set is a set of like couple of input and output. Or
Yeah, usually, yeah.
Thank you.
Yeah, so sometimes, well, forget about the inputs, but let's say sometimes this hidden node is missing. So whatever contribution this hidden node was making to the outputs, these other hidden nodes have to take over the role that this one would have had. Well, these other nodes have to compute. Somehow they have to compute whatever this would have computed. Yeah, so you have like multiple nodes doing the same thing somehow. Yeah.
How do you do this? Because it's randomly how to find the final solution with the random?
In the end, you have everything is present, but you multiply all of these weights by, let's say 20% of the nodes are dropped out. So you multiply all of these weights by 80%. And so the contribution that this node gets from all of these nodes is equal to the average of what it would get if you randomly chose 80%.
So the others chose the redundancy.
That's right.
couldn't understand what's this part. What's that mean with what's this part? It's so difficult to understand.
We can talk about it afterwards, but you assume that certain...
Yeah, I know this part.
Yeah.
But what's this part? With the same.
The probability of
the condition of
the data being produced by that network. Yeah. I better come back at the end. We can talk more about it. Good. Okay, so now we're going to talk about convolutional networks. Yeah, so convolutional networks, softmax, max pooling, and stride. And this will be, and then later on in week 5, we'll start talking about more about image processing. So the motivation for this is as follows. Well, it's easiest to think about this in terms of image classification. So there was this competition that ran over a number of years where they had a set of images. They had like a million images in 1,000 different categories. So they got photographs of pumpkins, photographs of cars, fire trucks, boats, dogs, cats, people, buildings, whatever. So a million images, 1,000 categories. So on average, 1,000 images in each category. And the task was to find some automated system which could take in an image and tell you what category the image belongs to. And previous systems were getting about 60% accuracy, 60 or 70% accuracy, and then in 2010, it's crept up over the years. It started out with 15% accuracy, and then 25, and then 30. Remember, you're picking between 1,000 different categories. And then eventually, in 2010, neural networks started to perform better than any other method on this task, which is partly what led to this big surge of interest in deep learning. And it was using what's called convolutional networks. So the idea behind this is as follows. Let's suppose one of the categories is bird. So let's say you're trying to decide whether the image is of a bird. Well, you might look to see whether there's feathers in the image. You might look at small parts of the image to look for a beak or an eye or a feather. And if you detect all of those things, then it lends evidence to the hypothesis that this is an image of a bird. But the feather, if you have a mechanism for detecting a feather in one part of the image, you can probably use the same mechanism to detect it in another part, because you don't know really where in the image the feather is going to be. And so we want to have, the idea is we have like a little window effectively that goes around the image, looking for feathers. And it's like a little mini neural network that uses the same weights in different parts of the image. That's the concept. And so these convolutional networks typically have this kind of structure that you have You have a convolutional layer, and then you may have like a downsampling layer, and you may have a couple of those, and then you have some fully connected layers, and then at the end you have several outputs, one for each category. Now, as I mentioned, this competition was based on ImageNet with 1,000 categories, but there are smaller data sets that maybe have 100 categories or 10 categories. There's this very small set of small images called CIFAR 10, where there's only 10 different categories and 60,000 images, and they're of a small size. So often we can test our methods on these smaller data sets before scaling them up to the larger ones. So this is what we're going to talk about. And as I think I mentioned in the very first lecture, this is one example where there's a very close connection between the structure and the actual brain. So this is connected to Hubel and Wiesel's analysis of the brain, where in the primary visual cortex you have neurons that respond to lines at particular angles, and then in the secondary cortex you have neurons that respond to sort of curved structures or bigger and bigger features, and they all kind of get combined in the cortex. So these are the components that we have in a convolutional neural network. We have convolutional layers. We have subsampling layers or pooling layers. We have fully connected layers, and we have an output layer. Now, the fully connected layers are of the same structure that we talked about before. The last couple of layers in this network look like the traditional 2 or 3 layer networks where everything's connected to everything, and you have this tanh transfer function. But these earlier parts have a different structure that we'll talk about now. So I mentioned that there's these smaller data sets. So one data set that's been very popular over the years is called the MNIST handwritten digits examples. So these were collected by the Canadian Postal Service back in the days when people wrote letters and they wrote the postcode on the envelope, and so they extracted, and they wanted to have an automated system for sorting the mail, so they extracted out these digits that people had actually written on their letters, and so these are several examples of each digit. This is the CIFAR 10 that I mentioned. So those are the 10 categories there: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. So automobile and truck are sometimes a little bit hard to distinguish because they have similar features. And these images are, I think, 32 by 32, so they're fairly low resolution. Okay, so let's just first briefly talk about the output layer. So if we only have two possible classes, then we can get away with just having one output, and then we can put that through a sigmoid to tell us the probability of the item being in that class. But if we have multiple outputs, so here, if it's MNIST or CIFAR 10, we have 10 different outputs. So the way we train the network usually is what's called the softmax function. And what happens here is the network has 10 outputs, Z 0 up to Z9 or Z1 up to Z10, and then the probability of, we calculate e to the power of each output. We calculate the exponential of each output, and it's assumed that the probability of that output representing the correct class is proportional to e to the power of that output. Not the output itself, but e to the power of that output. So the output could be positive or negative, but if I take the exponential, I definitely get a positive number. And the motivation for this is partly from physics of the Boltzmann distribution and so on, but it just happens to work quite well in practice, right? So when I say proportional, it has to be, for a probability, all of them have to add up to 1. So I have to divide by the sum of all those things to get, that's a normalizing constant. So when I divide by that, it guarantees that those probabilities add up to 1. And where the same way as we were talking about last week, we want to maximize the log of that probability. So the log of e to the zi is zi, and then we subtract off the log of that denominator. So this is something we want to maximize. So if we take the negative of this, then we can treat that as a loss as something we want to minimize. In other words, a loss function. So if the correct class is I, then we treat minus log probability of I as our cost function, and that's what we want to minimize. Now, again, there's a good explanation of this in the textbook, and there's an exercise on the website for you to go through, which I hope will help you understand this also a bit better. What this does in practice is the following. The first term here pushes up the correct class, right? The zi, so if the digit is actually a 2, then the output that corresponds to 2 will be that zi, so that'll be increased. And then this second term, what this second term actually does, it pushes down all of the others, but it preferentially pushes down the one that has the ones that have the higher activation. So if there's some other class which is wrong, but is being assigned a higher probability or nearly as high a probability as the correct class, then that's the one that will get pushed down the most, and the others will just get pushed down a little bit. In fact, every class is pushed down in proportional to its probability. Every wrong class is pushed down in proportion to its probability, the probability that the network assigns to it. And the correct class is pushed up according to 1 minus its probability. That's how this actually works in practice. Okay, so now we get to convolution. Now I'm going to work through an example here, but just show you a little bit the motivation of this. This actually comes from signal processing. When you process speech signals, you have continuous convolution using this formula. So then we convert that into a discrete convolution in 1 dimension, and then we convert it to a discrete convolution in 2 dimensions. Now, there's only really one. The main reason I'm showing you this is because there are 2 different conventions about the sign. You'll notice there's a minus sign here, and there's a plus sign here. So when we convolve 2 functions, we take integral of xa times w of t minus a dA. There's always this minus here. But in neural networks, we tend to use a plus instead of a minus. Now, the reason mathematicians and physicists like the minus sign is because it makes the convolution commutative. The convolution of x with w is the same as the convolution of w with x. That's a very nice mathematical property. when we switch to the plus sign, the thing is no longer commutative, but in neural networks we don't really care much about it being commutative. We just find it easier to deal with the plus sign when we write a computer program. Okay, so we're always going to be using the plus sign, but I'm just making you aware of this because you may see some sources that use the competing convention. Okay, so let me try to go to the document camera again. So let's say that this is our original image, and it's a color image. So it's got three, it's a very small image, it's only 7 by 5, and there's 3 different colors. So there's red, green, and blue, which I've written here, drawn here as 3 different layers. And then I've got what's called a convolutional filter. So the L is used in this equation, the L is used to index. Is that in focus? Yeah. The L is used to index the sorry, make it a bit, there's a bit of a glare here. I think that's a bit better even though it's darker. So L is used to index these different channels. So we call the red, green, and blue 3 different channels. And then the J is used to index the pixels. The J and K are used to index the pixels. And I think I'm... so there's J and there's K. So I'm currently computing... where are we? Yeah, so in this equation, I'm summing over the channels L, and I'm computing... yeah, okay, so this is the input layer, and then at the first hidden layer, I imagine that at the first hidden layer, I have an array of nodes like this. So this blue thing here is actually, the pink thing is the input, this blue thing is the first hidden layer. So the neurons in the hidden layer are also arranged in a rectangular grid like this. And I'm going to compute each of these, the activation of each of these nodes in this hidden layer one by one. So I'm going to start by computing this one in the corner. And it's not going to be dependent on all of the inputs. It's only going to be dependent on the pixels in a small neighborhood. So the activation of this node in the hidden layer only depends on this part of the image, this 3 by 3 component of the image, which is represented by this green square. And so this is what I'm computing. And so I have weights that connect, sorry, so many different layers here, but I have weights that connect those. So this green thing represents the sort of receptive field of that neuron, right? So I have weights connecting only those 9 only those 9 pixels to that hidden node, but actually there's 27 inputs altogether because there's 3 different channels, right? There's the red component, the green component, and the blue component. in each of those pixels. And I have certain, so to compute the activation of that blue node, I sum over J, I keep J and K fixed because J and K tell me the location of the blue node, but I use M and N to scan over this green area, right? So that's what these two summations here are doing, that N goes, in this case, from 0 to 2, 0, 1 and 2, and M also goes 0, 1 and 2. And I have a weight, the weight for this value is different from the weight for this value. Each of these has a corresponding weight. Okay, so I've got 27 different weights that I'm using to calculate this activation. I have a bias as well, and then after I've computed that linear sum, I put it through the activation function. Once I've computed that, and that completes the computation for that hidden node, then I move on to the next hidden node, and I repeat the process. And the key point here is, so K has now increased, and the key point here is that I use exactly the same weights in computing. I've shifted along my inputs, but I'm using the same weights to compute the next hidden node that I used to compute the first hidden node. So this is called weight sharing because the same weights are being used in every place. So I follow through these two sums with the M and the N to compute that hidden node, and then I move on to the next one. And I keep going like this for all the nodes in that top row. Now notice the number of hidden nodes in this row shrinks a little bit because I've sort of, by the time I get to here, I've banged into the edge. Now in a minute we'll talk about how to do padding and stuff, but just in this situation, there were 7, in the original input this had a width of 7, the hidden nodes will only have a width of 5, right? So J stays still and K moves up to here, and then when that's all done, then I come down and start doing the next row. J comes down here, and so on. So I compute that hidden node and then move along. And I continue this process until the thing gets down to here, at which point I've computed all the nodes in that hidden layer. All right, any questions about this? Does this make sense? Yes?
If you're just trying to fill in one box at a time, why do you need nine boxes?
If you're just trying to fill in one at a time, why do you need a 9? Why do you need a 3 by 3? Right, so this 3 by 3 thing is meant to show a subset of these pink nodes which are being used to calculate. These are not green nodes. The green is meant to show a subset of the pink nodes which are being used to compute the blue node. That's right. To compute one node in the hidden layer, you use 9 nodes in the input layer. Yes? Okay, so I think so the question was, these are good questions. So the question was, should the blue thing be here or should it be here? The answer is, I guess, conceptually, we think of it as being here in the middle, but computationally it's more convenient if this index n goes from 0 to something rather than going from minus. It's better if n goes 0, 1, 2 rather than like minus 1, 0, 1. It's just cleaner when we write the program. So when we write the program, it's actually like this, but we do think of it conceptually as being in the middle. Yeah, very good question. Yeah. So this is basically the way the convolutional networks work. And then this is from the input to the hidden layer. And then the same thing could happen from one hidden layer to another. Right, so we had 3 channels in the input. We could have multiple channels in the hidden layer. Yeah, we could have where are we? We could have 3 different channels in this hidden layer. We could have 5, we could have 10. It doesn't have to be the same number as we're in the input. It's totally independent. So often we have multiple channels, and they're all computed in exactly the same way, but each channel or filter has its own set of weights. Yeah, so if in the inputs we call them channels, in the hidden units we sometimes call them filters, right? But channel and filter is kind of interchangeable. Okay, so let's have a look at sort of the numerics of this. So let's suppose that the original image is has the dimensions of j times k, j by k, and that there's L channels. And let's suppose the filter is m by n. So in the example that I've shown you, j is 6, k is 7, L is 3, m is 3, and n is 3. And this just is exactly what I was just showing you, that the same weights are applied to each block. Now, if you want to figure out the size of the next layer, it's j plus 1 minus m by k plus 1 minus n. So in our example, the filter was 3 by 3. That chops off 2 rows and 2 columns effectively, because by the time the filter gets to here, we've bumped into the edge. Right? So this tells you the size of the next layer. So here's another example. So this is so in probably the very first network of this type was used in 1998, and there was a guy called Jan LeCun who pioneered this, and I think because of his name being LeCun, it was called LeNet, I think, so the LeNet architecture. So in the LeNet architecture, the first convolutional layer, the images were 32 by 32, these CIFAR 10 images, and the size of the filter was 5 by 5. So if you try to figure out the width of the next layer, it's 32 plus 1 minus 5, right? So it would be 28 by 28. And if there's 6 filters in that layer, we try to compute the number of weights per neuron, the number of neurons, the number of connections, and the number of independent parameters. So how many weights per neuron? Well, each neuron is receiving input from this 5 by 5 pixel part of the image. So that's 25 pixels. And each pixel has 3 color components, red, green, and blue. and then there's the bias, right? So there's 1 for the bias, and then plus 5 times 5 times 3, which is 76. So each neuron in the hidden layer is receiving input from 76 inputs. But they're all sharing, all the neurons in one filter are sharing those same weights. Now, how many neurons are there in that layer? Well, we just figured out that the width and the height of the layer is 28 by 28, and there's 6 filters. So the total number of neurons in that layer is 28 by 28 by 6. It's 4,704. How many connections are there in this layer? Well, you just multiply the number of neurons by the number of weights per neuron. 357,500. So you see we're starting to get to pretty large numbers here. Even though we're talking about small images, these numbers are getting big. 357,500. But because of the weight sharing, the number of free parameters is much smaller than that. The number of independent parameters is actually only 6 times 76, because in one there are 6 filters, and in one filter, all the neurons in one filter are using the same weights, and each neuron has 76 connections, so there's really only 76 parameters for each filter and 6 filters. So the total number of free parameters is only 456. Any questions about this? Yeah, and there's a exercise on the website for you to work through a similar situation. Let me just go back again to this slide. So the pooling. Sorry, here. Yeah, so this is the full LeNet architecture. So I think it's good to see the big picture of how this works. So we start with an image that's 32 by 32, and we apply this convolutional filter, 5 by 5. That layer has 6 filters, and each one is 28 by 28. So the size has been reduced a little bit. But then we use subsampling to reduce that to 14 by 14. And then we have another convolutional layer applied to the 14 by 14, again with a 5 by 5 window. That gets us to something that's 10 by 10. And then those things are fed into, that's subsampled again down to 5 by 5. And then we have 2 fully connected layers, and then we have the output. So this is the entire LeNet architecture. Now, what do I mean by subsampling? Well, it's done like this. In each, the thing is 28 by 28, but I break it into little groups of 2 by 2. And in each group of 2 by 2, I pick out the maximum activation of all the 4 nodes in that group. This is called max pooling. So you see here, you got 1, 1, 5, and 6. The maximum of those numbers is 6. You got 2, 4, 7, and 8. The maximum of these numbers is 3, and the maximum of those numbers is 4. Now, a lot of this is kind of tricks that was used for to get a higher score on this image classification competition. It seems at first a little unusual to pick the maximum activation, but I should also tell you they're using the ReLU. So they're not using the tanh or the sigmoid. They're using this special activation function that's 0 for negative x and identity for positive x. So it kind of makes sense to pick the maximum here. So these these features are trying to pick something out which may be present or absent. You know, if you think about, like, it doesn't quite work this way, but if it was looking for a feather, if it's on the left-hand side, it means that, you know, there's no feather there. And if it's on the right-hand side, the activation tells you how strongly it believes that there is a feather in that little region. And so if you think about it that way, this max pooling does kind of make sense, because the maximum number just tells you, like, you don't really care. You just want to know whether the feather is there. You don't really care whether it's a little bit to the left or a little bit to the right. So by maximizing these numbers, that kind of aggregates the evidence of there being any feather within that little region or whatever feature you're looking for. Yeah, so this max pooling. Yeah, so that's to get from the second layer to the next layer, is use the max pooling, and that cuts down the size of the layer. Then you do another convolution and then another max pooling, and then you got the fully connected layers. So this is a what a full convolutional network may look like. Okay, now as I mentioned, the size tends to shrink when you do this convolution because of the size of the filter. Now, depending on the situation, sometimes we prefer to preserve the size of the filter, the size of the layer, by, like, padding zeros around the previous layer. So this is called zero padding. Now, in this example here, we have one layer of zero padding, and so you'll see that the size of the next layer is actually preserved. Yeah, so I think in the padding, if you say, I think this was true in TensorFlow, I think probably also in PyTorch, if you say padding equals same, it means you preserve the size of the previous layer. So the previous layer was 6 by 7, and the next layer is also 6 by 7 because of the padding. Now, we'll go into image processing in more detail later on, but it's just interesting to look at this AlexNet as a example of this. So the LeNet was 1998, and then this is kind of what was the state of the art in 2012. This was the net that really performed remarkably well on this ImageNet database. And it's the same kind of architecture, but on a bigger scale. And they also were trying to squeeze out the GPUs then were not as big as they are now, so they're trying to squeeze out the maximum benefit from the GPUs that they had. So they used 2 GPUs, and the 2 GPUs operated largely independently, but had some interaction. So this diagram here, the bottom shows one GPU and the top shows the other GPU, and it's a bit hard to see these numbers, but if you look at this, if you blow this up and have a look at it, the original image is 224 by 224, so much bigger images. Then the first set of filters are 11 by 11, and then you have another set of filters that are, and you have 48 of those filters, and then you have 5 by 5 filters, and there's 128, 5 by 5, 128 filters that are 5 by 5, and then you do max pooling, and so on and so on. So it's just, you can look at the numbers, but everything's just on a much bigger scale. Now, another thing that they did well, again, a lot of this is just little sort of tricks and hacks, but they use max pooling with overlapping layers. So if it's just maybe kind of by chance that this works, but so this is the max pooling we were talking about. Like you take the maximum of those 4 numbers and then the maximum of these 4 and these 4 and these 4. So if you had a larger image, you would be looking at these 4 and then these 4 and then these 4. Now, somehow what they did with AlexNet, they took a maximum of 9 pixels, but then they shift this only by 2 pixels. So they look at the maximum of these 9, and then the maximum of these 9, and then later on the maximum of these 9. So it seems a bit funny because some numbers may appear twice. If this number happens to be very big, it may be the maximum of these and also the maximum of these. So the same number may appear twice in the next layer. But somehow this, did the job. So this leads us to the concept of stride. So right, so this example I showed you before, we just shifted that little green filter across by 1 pixel at a time. But if we want, we can move it like 2 pixels at a time. So what happens then is, okay, we calculate 1 blue pixel, and then we shift it across here to calculate the next blue pixel. And so this is called having a stride of 2. Yeah. So then the next layer would only have 12 neurons instead of whatever it had before, right? So the max makes the thing. This is another way of shrinking the size of the next layer without using max pooling. So I start with something that's 6 by 7, and then I go to another layer that's 3 by 4, right? Because the stride is 2, and this kind of makes sense because notice how every pixel in the original image still contributes to at least 1 hidden node. Every pixel will occur. So that that second column of green inputs it won't contribute to this node, but it will contribute to that first node. Yeah. So all the pixels get used somewhere. Yeah. So in this example, J is 7, K is 9, L and M are 3, but then M and N are 3, but the stride is 2. And then if you want to calculate the size of the next layer, it's 1 plus J minus M divided by S, right? And it's like integer division, because if you go off the end, you just assume that it's padded with zeros somehow. Right, so that's stride, and then if we put in, this is the sort of most general formula where you have padding and stride. So the padding is P, the stride is 2, the stride is S, and so if you figure it out, the size of the next layer is 1 plus J plus 2P minus M divided by S, and K plus 2P minus M over S. In practice, we usually don't memorize these formulas. We just kind of try to figure it out from the explicit numbers by figuring out what's the lowest and what's the highest place where the filter can be placed. So here's an example that uses padding and stride. Yeah, and this is taken from AlexNet. So in the first convolutional layer of AlexNet, the size of the image is 224, the padding is 2, the filter is of size 11 by 11, and the stride is 4. So what's the width of the next layer? Well, when you figure this all out, it's actually 55 by 55. And if there are 96 filters in that layer, we can calculate these numbers again. So how many weights per neuron? Well, the filter is 11 by 11, and there's 3 colors. So it's 1 plus 11 by 3. The stride doesn't make any difference to this. The number of neurons is, the geometry is 55 by 55, and there are 96 filters, so you multiply those numbers together. The number of connections, you just multiply those top 2 numbers together. So we're getting up to the serious sized network here, 105 connections. But the number of independent parameters is much lower, about 35,000. Because each filter, the neurons in every filter share the same 364 weights, and there's 96 filters. Okay. Any questions about this? So then just a couple of questions about overlapping pooling. So if the previous layer is size j by k, and max pooling is applied with width f and stride s, the size of the next layer is what? Well, again, it's 1 plus j minus f over s. So roughly speaking, you're dividing by the stride, but technically the details, you've got to look at the sort of fence post, avoid making a fence post error. So in the second layer of AlexNet, you have a layer that's 55 by 55, and they do max pooling with width 3 and stride 2. So what will be the size of the next layer? Well, we just apply that formula. It's 1 plus 55 minus 3 over 2, which is 27. I mean, if you just divide by the stride, you get a pretty close approximation. But 55 divided by 2 would be 22 and a half. It's actually a little bit bigger than that. I think it's 20. That looks funny, doesn't it? It looks like a mistake there. 55 minus 3 over 2. I better check that. This next one's a trick question. How many independent parameters does this add to the model? Well, the max pooling doesn't add any parameters because you're just taking the maximum of a set of values. So there's no parameter there to be tuned. And okay, so now that we understand all the components, let me just go back to this picture so that we can see the whole the whole picture. So what happens? Okay, so you got the original image here. These filters are 11 by 11 with a stride of 4. So this gets you something that's 55 by 55, and there's 48 filters here. And there's 2 GPUs, so this is being computed on the GPU 1, and exactly the same kind of thing is being computed on GPU 2, but with its own weights. And then you do max pooling. So the max pooling takes it from 55 down to 27. And then you have, you apply max pooling first, and then afterwards you have another convolutional layer which takes you from, with 5 by 5 filters, you have 128 of those, and it's happening on both GPUs. And then you do max pooling again, and then you have another set of convolutions, and this is the point at which there's an interaction between the 2 GPUs. So the values from that GPU somehow get copied to this GPU and contribute to this, and vice versa. But then after that, they operate independently again. So you go down to 13 by 13. So more convolutions, and then you have these dense layers where again there's interaction between the GPUs, and you're trying to distinguish between 1,000 different classes. Okay, so this is really possibly the first example of a real kind of industrial strength deep learning network, and at the time it took 2 days for them to train this on the MNIST. On ImageNet. And just right, so then this gets back to, we talked about the visualizations with the hint and diagrams. So people have tried to develop ways to visualize these hidden unit activations for these convolutional layers. And so what's shown here is actually, well, let's look at the first panel first. There's a first hidden layer. These are actually convolutional filters. So, you know, those little green filters I was showing you, each of these is one filter, and it's 11 by 11. So each of these small images is 11 by 11, and the size of the weights is shown in that 11 by 11. So yeah, the size of the weights is shown by the colors, and there's weights to the inputs in the red, green, and blue channel, so they're shown just by the intensity of the red, green, and blue pixel in that little 11 by 11 picture. So this gives us a nice way of visualizing those filters. And these, if you know anything about traditional image processing, these look a bit like what are called Gabor filters, or as I mentioned before, they're very reminiscent of these Hubel and Wiesel experiments. So this filter would detect a dark line in that at that angle with white on both sides, and a lot of them are like that. They detect a white line at a particular angle with dark on both sides. Some of them detect certain patterns of colors. So this would detect a region where the top part is more orange and the bottom part is more blue or whatever. So those are examples of some of the filters. There's 96 filters altogether. This is just some of them that are shown here. Now, if you look at the second layer, this is all being related back to the original image. So one way to explain this is saying, well, you pick a particular node in the second layer and you ask yourself, okay, which would cause this node to have its to be activated most strongly, right? And I think I mentioned this network was trained on images of cars, so you can see, you know, there's a node here which would detect a wheel in a particular location. You know, I think you could, you know, if there's a wheel here, or the fender of a car, or the hub cap, or the window, or different things. So you can sort of see some of the, this isn't the full set, but you can see some of the features that you would expect. And then this is at the third layer. Yeah, so this provides some visualization. There's one more topic I just want to briefly go through before we go, but first, does anyone have any questions about these convolutional networks? Okay. This is going to be very brief, only 4 slides. So I just want to say a little bit about PyTorch. Now, if you'll be having to, so for the first assignment, you'll be given some PyTorch code, and you'll be asked to fill in, you know, parts of the code that are missing, or modify some parts of the code. So Alex Long, the course administrator, has put a notice up here, some resources here for you to go and learn about PyTorch. So I recommend that you do that. So I'm just going to give a very brief overview of this. Okay, so this is the typical structure of a PyTorch program is like this. So you create a certain, you define a certain network architecture based on the module class in PyTorch, and then you declare a network to be of that type. So if you define a structure called my network, then you'll say net equals my network. If you're using a GPU, you have to say you define the device and you say to device. So most of you probably will be using a CPU rather than a GPU. If you're using a CPU, you may not have to say the to device, but I'm just making you aware of it if you have a GPU and you want to use it, or if you see code that uses a GPU. Yeah. Then you have components which will load the data for you. So typically you'll say train loader equals torch.utils.data loader, and then give it some parameters. And the same thing with the test, if you have a separate training and a test set. So with the MNIST and the CIFAR, typically we have a training set of 50,000 and a test set of 10,000, let's say. And so this is the nice thing about PyTorch, is it tries to kind of abstract away or take away a lot of those sort of details and make it easier to, excuse me, I mean, you know, one of my PhD students was saying the other day, you know, you think about Alex Zelinsky and Hinton, they had to build that network without all of these sort of fancy tools, so they had a harder time of it in a lot of ways. Yeah, so the data loader will handle stuff like automatically putting the data into mini batches, for example. Yeah, that's, you don't have to kind of worry about that. You just tell it what you want it to do. Then you decide on an optimizer. So the two So the optimizer might be stochastic gradient descent. So the two most common ones probably that you would be looking at is stochastic gradient descent, which is just a fancy way of saying backpropagation, or the Adam optimizer is often used as well. So you just put Adam in there instead of SGD, and then you may give it some parameters. So you set all of that up, and then you have a cycle typically where you do some training. You train on a mini batch. You train all the data in one epoch. That's one training cycle, and then you may try it on the test data so that you can plot both the training data and the test data. So PyTorch program typically will have this kind of structure. The network extends the class torch.nn.module. So you'll have an init method, which will, normally you'll call the init method in the module class, and then underneath that you'll have some code that defines the structure of the network. Normally a series of layers, a linear layer, and then you have the activation function, and then you may have max pooling or batch normalization, or you just fit all of these things in to define the structure of the network, and then you have a forward pass, so that tells you what to do when the network is applied to some input. And then the train part is typically like this. Right, so this trains, this is supposed to go through, this is supposed to be one epoch, so it's supposed to go through all of the training data once, and it uses the data loader to break the thing up into mini batches randomly. So you just call enumerate train loader, and it'll give you those mini batches one at a time. It'll give you the input and the target. And then, so here we zero the gradients. And this is partly, I guess this is probably one of the things that makes PyTorch a lot nicer than, for example, TensorFlow, is that you have much kind of better control over the way these gradients work. So the gradients are calculated automatically. So I don't have to, in my network, I just define the equations that will do the forward pass on the network. I don't have to calculate the derivative myself because PyTorch will do that for us. Right? So when we create this network, it creates the weights, and then for every weight, it automatically creates gradients for each weight. And so when we say 0 grad, that means I want you to set all the gradients in this network to 0. And then when I say output equals net of data, it computes it applies the network to the inputs and computes the outputs. And then I compute the loss function. So the loss function might be, softmax, typically in this case, or it might be the mean squared error. And then I do loss.backward. So when I do loss.backward, it automatically computes the gradients. And it automatically computes the gradients and it accumulates the differentials. So, like I say, every weight has a corresponding gradient. So, if I call loss.backward multiple times, well, sorry, when I do 0 grad, it sets the gradients to 0. If I do loss.backward, it adds those gradients to whatever you had before. So if I call loss.backwards multiple times with different loss functions, it'll just accumulate those gradients, but not actually changing the weights. And then it's only when I call optimizer.step is the point at which it actually updates the weights based on the gradients. So you've got this nice kind of low-level control over the process. You know, setting the weights gradients to 0, backpropagating, and applying the optimizer. And we talked about momentum. So if you specify that there's momentum, it'll handle that all as well. That'll be handled in the optimizer step. Now, there's a sort of explanation in the textbook about what's happening in the background. We don't have to worry too much about the details, but the nice thing, it creates what's called a computation graph. And if one so in order to calculate the gradients, it has to keep track of which variables depended on which other variables. And if you reassign a variable, it may have to keep the old version of the variable as well as the new one. And there's all this kind of stuff that goes on in the background, but it handles all of that for us. And if there's a variable that's no longer needed, it'll do garbage collection and throw it away. So again, this is sort of the nice thing. It handles a lot of these tedious details for us. And then the testing, right, so this is typically what the testing would look like. Now, there's two things. Okay, so torch.noGrad. So what the torch.noGrad does is it says, okay, within this block, I don't want you to calculate the gradients. Now, sometimes that's just used as a kind of safety measure to make sure that we're not training on the test set. Yeah, so with machine learning, we always want to be very sure that we're not using the test set for training, that we're only using it for evaluation. Now, if we left out this thing that says with torch.noGrad, it might be okay, because if we don't call, let's say if we don't call loss.backward, then it won't change the gradients. And then if we later say 0 grad, it'll throw away whatever gradients it has. So if we left out this with torch.noGrad, the thing may still work correctly, because we haven't updated, we haven't called loss.backward in here, right? But it's better if we put in the with torch.noGrad, because that makes it absolutely certain that we're not training on the test set in any way, right? I'll come back to the eval and train in a minute. Now, in this loop here, right, so normally we have a test loader. Normally the test set is large enough. It also has to be divided into mini batches. So we have a loader that feeds those to us one at a time. We apply the model, we calculate the test loss, and typically we print the test loss, right? We're not backpropagating on it, we're just printing it. And just, finally this eval thing. So I mentioned about dropout, and there's this other thing called batch normalization, which we'll talk about batch normalization in week 5, but let's just think about dropout for the moment. So with dropout, when you say net.train, that switches the network into a mode where so remember there's two things with dropout. So if you do net.train, that means until further notice, I want you to apply dropout by randomly removing a certain percentage of the nodes, right? When you say net.eval, that says until further notice, I want you to deal with dropout by having all the nodes present, but multiplying all the all the weights by the same percentage, right? So this is what's actually used to toggle between those two modes, where you're actually dropping out the nodes and when you're just having all of them present but multiplied by the factor. And so we can explicitly toggle back and forth. So the no-grad and the train eval do similar things, but there are situations where we may want to operate them independently, and PyTorch gives us the flexibility to do that. There's also, so when we get to batch normalization, this thing also toggles the way batch normalization is applied. So when we get to that, you'll understand that. So the eval and train thing toggles back and forth, but both the norm and the both batch norm and the dropout. The no grad just tells the network not to compute gradients. Okay, any questions about this? Good. Okay, I think we can we can go 8 minutes early.
You wouldn't have time next Monday, would you? It's the Labor Day.
I won't be in on Monday. I mean, like,
But the problem is during the day, tied up in the CBD.
oh, right. Yeah, okay. We could meet in the evening sometime.
That makes sense. Yeah, that makes sense. Like around 6-ish or something.
Yeah.
Then I will shoot you an email.
Yeah, so I mean, I could even go into the city potentially, or either
That
way.
works for you.
Yeah, on my way out.
Yeah, that's convenient. No, I mean, it's just fascinating. I thought you'd be stunned at the similarities between. I don't know what the reward. The name for reward function-based learning is.
Oh, yeah, the reinforcement.
Reinforcement learning. You'd be stunned at the similarities between that and macroeconomic theory. You'd be stunned.
Really?
You would be. You'd be absolutely stunned. It's the exact same in most macroeconomics models, dynamic stochastic general equilibrium models. You assume an agent which maximizes utility over a dynamic system effectively over time, and it is the math is exactly the same. Exactly the same.
There's this, I forget
It's
his
identical.
name. There's like a control theory
Yeah,
guy
that
who
everyone's
wrote about
based-
all this
yeah.
stuff back in the in the 80s, and did it more rigorously. And
Yes.
stuff.
It's
He's kind of frustrated that his work didn't get more attention. What was his name? I'll find out. Yeah, one of my students has read some of his papers.
it's incredible. Like there's this guy that was this guy at Northwestern. I think he's in Harvard now. Who was talking about using econ, not Parks, but no, also Parks.
Okay.
David C. Parks at Harvard. He also did
Yeah.
an article in Science about using economics as a framework for governing AI behavior.
Right.
And all these rich findings and stuff in the field. This was for humans, but very useful computation analysis. Anyway. Welcome. Thanks
Yes,
very much.
everybody will.
Yeah.
I have one question. Simply speaking, every filter is designed to capture some feature,
Right.
advanced feature. So how do you decide the number of filters, and do you have to manually design it?
That's a good question. I mean, you have to manually, basically you do it based on experience. I mean, but I will say one thing, like if you, I mean, if I can go back to, if I can go back to some of these more convolution. Like it's based on experience, but you'll notice something interesting here. Often, as in the different layers, you see the layers get smaller, but the number of filters gets bigger. So there's actually a kind of balance. If you multiply the number of features by the size, it's kind of more or less constant, not quite, but there's this, you see this trade-off. Yeah, you get the size of the layer gets smaller, but the number of filters gets bigger. And then eventually you have just the fully connected layers is like everything's collapsed to a point, but then you have lots of features. I mean, some of these networks are a bit, sometimes they have like, in my opinion, too many nodes in the fully connected layers. Like there's a kind of imbalance. Like when we get to the details of AlexNet, a lot of the nodes were in these fully connected layers, which I think might have been overkill. But roughly speaking, the number of weights in each layer should be similar, I think, yeah.
Just one
Yeah,
question.
yeah.
I'm like in my last 2 semesters, so
Yeah.
I was looking for some research project opportunity. So I was wondering if you have any opportunity.
Yeah, I'm having to think about this. I may be able to. So you look at something next term or the term after or something. Yeah, someone else was asking. Yeah, I'm trying to come up with a few projects. I know someone sent me an email. I haven't responded yet. I've been very busy. But if you do send me an email, I will try to get back to you. A lot of, I'm mainly interested in generative models these days, like variations on GANs.
Oh,
We're going to get to at the end of
yeah,
the
I know that.
GANs, yeah. So, if you, yeah, I apologize, I've been slack responding to some other people, but if you send me an email, I will try to get back to you about it. We can discuss some possibilities.
Yeah, sure. I will
Yeah.
get in touch. Okay. Thank you.
Sure.
Okay. Does it means like the first few layers capture more detailed features, but the later quite feels they will capture more general feature of whole the picture?
That's right. I think the early layers capture simple, localized features.
It's like just capture the line or
Yeah.
corner feature, but the last layer they capture whole the feature of the whole.
That's right.
It's
The
like
early
exact.
layers, it's like localized,
Uh-huh.
but by the time you get to the deeper
Yeah,
the
you
layers, you
capture all
capture
the
features from a
whole-
bigger and bigger part of the image, and eventually the whole image.
Yeah, but if we want to use the transfer learning to do the fine tuning of our model, it
Yeah.
seems that we can just use the first couple layers, but just change a little bit for the last layer for our data set.
Yeah,
That's
so
correct,
the
that's
way the transfer learning, the most common way, people tend to use AlexNet, and they pull off. Yeah, so what normally
I just-
happens is people take off these layers and replace
for the
it.
clear layer to
They
the new
replace it
one.
with something else.
Um,
And then I think they normally, when they train, they allow everything else to change as well, but they start with the initial weights from the.
But if I want to change the couples first, like the first 2 or 3 layers, I